Okay, second revision video for P1. We're going to look at the spec points for heating buildings and efficiency. So to start off with, we're thinking about U values, and you need to know that they measure how effective a material is as an insulator. So you are looking for the lower the better when it comes to U values. If it's low, it means that the material you are looking at is a better insulator. So they may give you 2 windows, double glazed, triple glazed, with 2 sets of U values, and you'd be asked to pick the best window or recommend the best window, and we'd be looking for the window with the lowest U value on it. That would indicate that it was a better insulator. Okay. Then you need to think about solar panels. Now, solar panels can contain water actually themselves, and which is then heated by the sun's radiation, and that water can then flow around your hot water system to keep your building nice and hot, or it can directly supply the hot water to your house. Either of those two things. However, just remember that solar panels are not that efficient. We don't live in an area where we have sun all year round, so when it's not so sunny or it's a bit cloudy, this is not going to be very efficient. Okay. You also need to calculate specific heat capacity in this exam. You are given the calculation on your data sheet, so please use it. It's just a case of swapping those numbers in. So here you can see that you've got the specific heat capacity of water is 4,200 joules per kilograms degrees C. We define the energy needed to heat 3 kilograms of that water from 5 to 60. Okay, so we've got energy transferred is E equals the mass, which is 3 kilograms, by a specific heat capacity of water times by the temperature change. So from 5 to 60 is 55, and then we get the answer in joules. Okay, rather large number, but obviously we could convert it to kilojoules if we needed to, or the exam required. So specific heat capacity, although it's given there, is just the amount of energy needed to change the temperature of 1 kilogram of a substance by 1 degree C. Okay, that is a specific heat capacity. You'll need to calculate it, but again, you are given the formula, so do not worry too much about that. Okay, but obviously thinking about energy transfer, the amount of energy you're getting out of things and different appliances in the house, it's worth just noting that we might need to consider payback in some of these questions that are talking about solar panels or triple glazing, linked in with maybe some specific heat capacity calculations. Just bear in mind that solar panels, triple glazing, etc. is expensive. It's expensive for the client to put it in. However, over time, they may reap those rewards in saving. So you'd be doing cost divided by the saving that they'd achieve will give you an idea of how many years or months or even days it might take to then get that saving back out of the cost you've had to put into the stuff you've put in your house. Okay, so you might need to consider payback time in some of those exam questions, just to give you some evidence and support what you're trying to say. Right, importantly then, we need to note that energy can be transferred usefully, just stored, or dissipated, just spread out. So it's not very concentrated. It can't really trigger a new energy transfer, but it is then anything that's dissipated just tends to warm up the environment really. We cannot create it or destroy it though. Okay, very important to note. You need to learn all the different types of energy. Okay, I recommend to use, most kids hate learning GCSE energy names as a bit of a mnemonic to help you remember. Okay, the first letter then, and all of GCSE, stands for a form of energy. So magnetic, kinetic, movement, heat or thermal, light, gravitational potential, chemical sound, electrical, elastic potential, and nuclear. Okay, easy way of remembering those energy names, and you'll need those because we'll look at the next topic, looking at energy transfers of appliances. So for example, a light bulb transferring the electrical energy into light energy. Okay, thinking about that then, you may be faced with what's called a Sankey diagram. Sankey diagram basically represents the amount of energy an appliance may use or waste. Okay, so in this case, if it was a light bulb, it had 100 joules of energy coming in. 10 joules of it is useful, was light, but 90 joules is actually being wasted here. And you may need to calculate either of these two numbers, or in fact the number coming in. So it might be a simple subtraction. So imagine that wasn't present. 100 joules coming in, 90 is being wasted, so I know there's only 10 being left as useful. Or it could be overlaid over some graph paper, and you could have to count the squares to work out what they represent for each end. So you'd you definitely get a known end. You'd see how many squares there are, how much is coming in, divide that by the number of squares to work out what each square is worth, and then you can count up those squares at either end here to calculate it. So they are often shown to scale with these Sankey diagrams, and from that you can calculate the efficiency of an appliance by using these equations, which again are on that data sheet you get in the exam, so there's no need to remember them. The efficiency of an appliance, so if this was a light bulb, you can already see it's not very efficient, it's not great, we've got a ridiculous amount going off to form heat. So we've got useful energy out, which is 10 joules, divided by the total energy in, which is 100, times by 100 to get it into percentage, would give us the efficiency of that light bulb. Okay, again, it might be in terms of power or watts, but it would still be exactly the same process. Okay, so we've looked at U values, the lower the better. We've talked about solar panels, and then any other, so like your triple glazing, etc. Think about payback, how that might be able to support your answer for an exam question. Calculating specific heat capacity, looking at different types of energy names, and then looking at Sankey diagrams and calculating efficiency from that. Okay, so that's the end of chapter 2.